Hey everyone, and welcome. Today we are jumping right into the really fascinating science of biological sex. We're going to explore it by looking at a set of clinical conditions known as disorders of sexual development, or DSDs. And trust me, this is going to give us a much clearer and honestly a much more complex picture of how human biology actually works. So let's get into it.
So let's just kick things off with a huge question. What really determines our sex? Now, if your first thought is simply X and Y chromosomes, you are definitely in for a surprise today. The biological story, as you're about to see, is way more intricate than any simple on or off switch. In reality, biological sex isn't a single event at all. It's more like a whole cascade of events that have to happen in just the right sequence. Clinically speaking, we can break it down into at least 7 different layers. It starts with our genes and chromosomes, which then guides how our gonads develop. Those gonads release hormones, which then sculpt our internal and external anatomy. It's this incredibly complex chain reaction, and every single step is critical.
Okay, so here's our game plan. First, we're going to talk about sex as a spectrum. Then we'll get into what happens when that development varies. We'll spotlight some specific examples, first with chromosomes, then with hormones. And we'll wrap it all up by looking at how these conditions are diagnosed and what the pathways of care look like. All right, first up, the spectrum of sex. Because really, before we can even begin to understand the variations, we've got to move past that simple male-female binary idea that most of us were taught in school. The clinical term we're going to be using throughout this is DSD, which stands for Disorders of Sexual Development. Now, this is really just an umbrella term that medicine uses to describe a group of conditions where the development of chromosomes or gonads or anatomy follows a path that's considered atypical. And listen to this. This is not nearly as rare as you might think. We're talking about an incidence of roughly 2 in every 1,000 people. What that tells us is that variations in sexual development are a natural, consistent part of human biology. The whole goal here is to understand these variations, not to stigmatize them. So if these variations are a natural part of biology, how do doctors and scientists make sense of them all? Well, that brings us right to our next section, how these different developmental pathways are actually classified. Modern medicine tends to put DSDs into 3 big buckets. First, you've got the sex chromosome DSDs. This is when there's a variation in the chromosomes themselves, like having too few or too many. The other 2 categories are for folks who have the typical 46XY or 46XX chromosomes, but their development diverges at a later stage. And we are going to look at some key examples from each of these. Let's dive into that first group, the cases where the variation is right there in the genetic blueprint itself, the chromosome DSDs. A classic and really important example of a sex chromosome DSD is something called Turner syndrome. It's actually one of the most common chromosomal conditions we know of. Okay, let's break this down. The karyotype, which is basically just a picture of all your chromosomes, is 45X. That means there's just a single X chromosome instead of the typical 2. Because of this, the gonads don't fully develop into ovaries. Instead, they often remain as fibrous tissue, sometimes they're called streak gonads. And probably one of the most common physical signs is short stature, usually under 150 centimeters or about 4'11". There can be other physical features too, like webbing of the neck or broad shield-like chest. And internally, since the ovaries are undeveloped, individuals with Turner syndrome usually experience what's called primary amenorrhea, which just means menstruation doesn't start at puberty. It's also super important for them to be monitored for potential heart or kidney issues. Okay, another really well-known variation in that chromosomal blueprint is Klinefelter syndrome. Now, in this case, the chromosome map is 47XXY, so there's an extra X chromosome. This variation typically leads to the development of small, firm testes. Some of the key features can include a taller, leaner build, what's sometimes called a unicoid build, and sometimes breast development, which is clinically known as gynecomastia. And because of these differences, infertility is pretty common. All right, let's totally switch gears. We've just seen what can happen when the genetic blueprint itself is different. But what happens when that blueprint is typical, but the body's chemical signals, the hormones, get all mixed up? This brings us to the world of hormonal DSDs. One of the most fascinating examples of this has to be androgen insensitivity syndrome, or AIS. And it's fascinating because it perfectly shows the difference between our genes and our actual physical bodies. Okay, this is where it gets really incredible. A person with complete AIS has a 46XY karyotype. They have internal testes, and those testes produce testosterone. But, and this is absolutely the key,
Their body's cells are completely deaf to that testosterone. They have the hormone, but they can't respond to its signals. So their external development follows a female pathway. They develop breasts at puberty, but because there's no uterus, they won't menstruate. That lack of response to androgens also explains why there's usually very little, if any, pubic or underarm hair. So you can imagine how this could be a real diagnostic puzzle, right? A doctor might see a teenager who hasn't started her period, and an ultrasound shows there's no uterus. Is it AIS, or is it a totally different condition called Mullerian agenesis, or MRKH? Well, the key difference lies in the chromosomes and the gonads. MRKH happens in 46XX individuals who have ovaries, while AIS, as we just saw, happens in 46XY individuals who have testes. Now let's look at just one more example, and this time it's a condition that can affect individuals who have 46XX chromosomes, congenital adrenal hyperplasia, or CAH. Okay, CAH is an inherited disorder that messes with the adrenal glands. The best way to picture it is like a factory assembly line. A really important enzyme is missing, which creates a roadblock in the production of a vital hormone, cortisol. So what happens? Well, all the raw materials before that block get backed up like a traffic jam. And the body reroutes that traffic jam of materials down a different path, where they get converted into excess androgens, male hormones. In a 46XX fetus, all those extra androgens lead to what's called virilization, which is the development of male characteristics. So all of this naturally brings us to our final section. How are these complex conditions actually identified? And what does the care and support system look like for these individuals and their families? Well, diagnosing a DSD, especially in a newborn, is a really careful step-by-step process. It takes a whole team of specialists. It usually starts with a physical exam, of course, but the team very quickly starts looking deeper. They'll use imaging like an ultrasound to see the internal organs. At the same time, a genetic test called a karyotype reveals that chromosomal map we talked about, and blood tests are run to check all the key hormone levels. It's all about putting these different puzzle pieces together to see the whole complete picture. And that team approach continues right into long-term care. The single most important principle here is that care has to be highly individualized. There is no one-size-fits-all path. Really complex decisions like gender assignment are made incredibly carefully with the family, looking at things like future function and fertility potential. Treatment might involve hormone therapy to help support development during puberty, and the timing of any potential surgeries is a huge point of discussion. But above all else, a compassionate, multidisciplinary team is the absolute gold standard of care. So we end with this question to think about. How does understanding this incredible science, this complexity, expand our view of human diversity? What this science really shows us, loud and clear, is that biology isn't a simple binary. It's a vast, diverse, and beautiful spectrum. And exploring that science, I think, gives us a much richer appreciation for all the different ways there are to be human.